So we're given this vector called A and this vector called B. And the y component of B isn't known. So all we know is that it's an integer and we're calling it M. And the task is to find the value of M. Now, obviously this information alone isn't enough to actually work out what's going on. So we're actually given a further bit of data. And so what this requirement tells us is that if we project A onto B, that's a terrible arrow, isn't it? If we project A onto B, the result will be this vector. And you can see here, this is actually B tilde. And so the idea is that when we project onto B tilde, we get this number popping out the front. Okay, so in order to visualize that, we can just draw a quick little graph. We'll just do it in 2 dimensions to kind of get the idea. So here's B tilde, here's A. And the idea is that when we project A onto B tilde, we get this vector here, which is negative 11 over 18 times B tilde. Okay, so that's kind of the idea. And so the first task is to find this value of M. So basically this y component of the vector B. Now to do this, it's a lot easier to proceed if we actually give proper names to each part of the information we're given. And that's because there's hidden data actually in the question that's quite hard to express unless we name things. And the hidden data in particular is this word the. So find the value of M. So basically we're told that, you know, these conditions here uniquely pin down M. And so if we can find any M that satisfies these conditions, it is the value for M. So to exploit this uniqueness stipulation, we're going to write out the question again, and we're going to try and write it very clearly. And that way we'll have the notation necessary to fully exploit this hidden data about the uniqueness of M, okay? So let A tilde denote the vector given. I'm going to use component notation because I just find it a bit easier to read. And we'll also let B tilde of N, and I'll write it with a capital just to distinguish it from this. Let B tilde of N denote this vector up here, but with this M replaced by this parameter, okay? So 1, N, negative 1. And I wrote that as a capital just so that later we can let B tilde equal capital B tilde of M. So this M will be the specific value we find, whereas this N is really just a dummy variable. So really I want this to be true for every possible N. I don't want it to just be true for the specific M that we find, okay? So that's why I've set things up like that. I'll also let P of N denote this condition here. And so really it's saying that, so the vector resolute of A tilde in the direction of B tilde, well, that's the projection onto B tilde, and I'll write it with a capital because that's how our notation has been set up here. The projection onto B tilde of A tilde, it equals this. So it equals negative 11 over 18 times B tilde. And arguably here, I should really be writing, you know, the if and only if symbol. Because basically this is a boolean, this is a bool, and this is also a bool. And so by convention, a quality of booleans is denoted like this. Now there's also a little bit more information given. So we want to start off by assuming that P of M is true. So this M is not a dummy variable. It's literally the M that we're trying to find. And remember, we've got this uniqueness stipulation. So there's only one value of M that satisfies these conditions. And so what this tells us is that we can also assume that for any number N in the integers, if that number has the property of interest, then the number we're looking for, so M, the number we're looking for has to equal that number N that satisfies P of N. Okay, so this is the one we're looking for. This is the one we found that has the property of interest. And this is just saying that if it has the property of interest, it's the number we're looking for. So if you want to just think of that, if you want kind of a summary of what this line means, what it's basically saying is that P holds for only M. It doesn't hold for anything but M. Lastly, we'll just let B tilde with lowercase equal B uppercase, evaluated at this special number M that has been pinned down, firstly by saying that it has the property of interest, and also by this mention of M, which is really saying that M is the only thing with this property. Okay, so to begin the problem, we need to manipulate P of N. So that's this statement, which remember is just our improved version of this statement. So let's go ahead and manipulate that. Okay, so P of N is equivalent to, we just use our formula for vector projections. So that's A tilde dot product with B of N divided by the magnitude of B of N squared times the vector itself. So that's literally the definition of what this notation means. And then we need an equal sign over here. And then we just copy this out, right? Negative 11 over 18 B of N. And I should have an N here. And so this is obviously equivalent to firstly just the result of slashing these out. We don't need those vectors anymore. And also I'm just going to rewrite it so that we don't have this multi-line stuff. So I'm going to move this to the other side, and the division by 18 will also go to the other side. Okay, so we're going to get 18 A tilde dot product with B of N equals negative 11 times the norm or absolute value or magnitude of B of N squared. So let's go ahead and work these out. To find A bullet B of N, it's pretty straightforward. We use the definition here. So 2 times 1 is 2. So I'll put 2 there. We also pick up a negative 3 times n, so minus 3n. Ooh, the colors are getting very strange. So minus 3n there. And then, over here we have the 1 and the negative 1. So we pick up a minus 1 here. And that simplifies to 1 minus 3n. Okay, so P of n is equivalent to 18 times 1 minus 3n equals negative 11 times 2 plus n squared. And so you should be able to see that this is going to turn into quadratic. So just expand this out on the left, expand out on the right. We'll put everything on the left-hand side. So we're going to get 11n squared minus 54n plus 40. And that equals 0. Now at this point, what you want to do is you want to move to scratch work. Let me put that word in quotes. Scratch work. So that means you're doing some working that isn't actually part of your main proof, or let's say it's not really part of your main solution, but it's something to do on the side to kind of work out what your next step should be. Okay, so in particular, finding an integer solution to this doesn't actually need to be part of your actual proof. It can just be done on the side. And when you do that, and I'll show you how to do that in a moment, but when you do that, you find that P of 4 is really the thing we should be computing. Okay, so this turns out to have an integer solution of n equals 4. And so therefore, demonstrating that P of 4 will actually solve the problem for us. So let's have a look at how that works, and then I'll show you guys a little bit later how you actually come up with this 4. So P of 4 is equivalent to 11 4 squared minus 54 times 4 plus 40 equals 0, which is equivalent to 176 minus 216 plus 40. And we'll just add these two together. That seems to be the easiest way to see the answer. So we get 216 minus 216. And this statement is obviously true. Okay, so So P of 4 is true. So it turns out that because we've shown our condition P is true of the number 4, that actually allows us to conclude that M equals 4. Okay, therefore, M equals 4. And if you're wondering why that's true, now keeping in mind I still haven't shown you how to come up with this 4. But before I show you how to come up with that, because that's kind of on the side, that's on a different bit of paper, really. Before I show you that, let's just clarify the logic here. I mean, how is it that showing that P of 4 is equivalent to true, how is it that that lets us conclude that M equals 4? Okay, and it really comes down to this word, the. There's only one solution to our problem. And that was encapsulated, if you'll recall, in this line. So we said that for any n in the integers, if P holds for that n, then the number we're looking for has to be that number n. And so really, the ability to do this step is a special case of this principle. And you can actually see that, right? So this is saying for all n in the integers, P of n implies m equals n. So as a special case, we should be able to infer that P of 4 implies m equals 4, because this is true for all n in Z, and this is just a special case where n equals 4, right? And so we've got this P of 4 implies m equals 4 here, but remember, we just showed P of 4. So we've done that, we've shown it's true, right? So we've shown the premise in our implication, and therefore we get to conclude the conclusion. And if you wanted to be really clear, you could even give these names. So, you know, call this alpha and call this beta. Call this beta. And then to explain how you did this step, you could say, well, using beta. As a special case of beta, it follows that m is 4. Okay, well, we're not going to do that. I don't think it's necessary to add that much detail into the solution. But that could definitely be done if you really like just being clear about how you're performing the inferences that you're performing. So in summary, this is a complete and correct solution that shows that m equals 4. We've gone from our assumptions as formalized by this, and we've moved deductively to show that there's only one possible value for m, and it has to be 4. So that actually completes the proof, and it completes the problem. But the problem is, from your point of view, it's not clear how you would have known to compute P of 4 here. So the fact that we chose 4 here really helped us write the proof, because we ended up getting true out here, and that in turn allowed us to invoke this condition. But if we'd chosen any other number like 3 or 5 or -5, well, we would have gotten false out here. And so that really would not have helped us finish the problem, and we would not have been able to conclude this last line. So how do you actually know to look at P of 4, right? So that's what we'll look at now. And what I want to do is really just copy this quadratic. Copy this quadratic here. Let's paste it there. So let's go ahead and give this a name. And we should keep in mind that right now we're doing scratch work. So the teacher really doesn't need to see this. And in fact, we don't have to be rigorous in scratch work, because it's not actually part of the proof of the correctness of our solution. It's just something we do on the side to work out, you know, how to proceed, how to realize that 4 is the right number to plug in here, right? So we need to solve this quadratic in order to find that n equals 4 is the only integer solution. And so to do that is actually pretty hard without a calculator, right? So you could try computing delta, so that's b squared minus 4ac, and you'll get some god-awful number, some huge number, and then you'll be stuck trying to find the square root of that number. And that's just too hard. I mean, I don't know of any really good algorithms for finding square roots of, you know, multi-digit numbers. Maybe there is one out there, but I just don't know of one. So I'm not going to teach you that technique because I think it's too hard. So instead what we're going to do is we're going to use something called the rational root theorem. Now I'm cautiously optimistic that you guys have seen this before, but if not, let's just go over it. So this is a theorem about polynomials with integer coefficients, which is what this set refers to. So this is the set of all polynomials in X with integer coefficients, okay? So an example element would be, I don't know, x cubed minus 5x plus 1, something like that. And what it tells us is that supposing we have an x star that's an integer, and supposing that x star is actually a root of f, then it has to be the case that x star is a factor of the constant term of f. Okay, so in this context, the constant term of f would be 1, and so the factors of 1 are plus and minus 1. And so therefore we can conclude that the only way this polynomial can have an integer root is if that root is either plus 1 or minus 1. And in fact, you could even plug those numbers in and you can see that they don't work. And so for this particular polynomial, it's pretty clear that, based on this theorem, there are no integer roots. So let's go ahead and use this theorem on the polynomial that we're interested in. So in particular, the constant term is 40, and therefore what we want to do is we actually want to find the factors of 40, because every integer root of f is going to be a factor of 40. And actually finding this set is pretty easy, right? Because, well, we know 40 factorizes as 8 times 5, and so therefore all the factors of 40 will either contain a 5 or they won't contain a 5. So half are going to contain 5, half won't. And using that, we can list all the factors pretty easily, right? So let's start with the ones that don't contain a factor of 5. So plus or minus 1, or plus or minus 2, or plus or minus 4, or plus or minus 8. Union, and now we'll list the ones that do contain a 5. So plus or minus 5, or plus or minus 10, or plus or minus 20, or plus or minus 40. And so if this f we're looking at has an integer root, it has to be one of these, right? So in principle, we could go ahead and just compute, could find f of 1, find f of negative 1, find f of 2, find f of negative 2, and just keep going through all the factors until we find our integer root. And it turns out that when we get to 4, and once we plug it in, actually it'll literally be the next one, f of 4, we're going to get 0. And so that's how we know that 4 is the number we needed up here to plug into here, right? Now the problem is really that technique just takes a bit too long. So we have to plug our number, we pick our candidate root, we square it, we plug it in here, we multiply by 11, we plug it in here, we multiply by negative 54, we add a bunch of things up, and that's just to test one of these numbers. And, in principle, I mean, there's 16 numbers here, and so that could take quite a long time. And in an exam situation, we really don't have time to be stuffing around trying up to 16 different candidate solutions, especially with these fairly big coefficients. It's really just going to take far too long. So what we do is we actually don't rush straight into computing f of these numbers. So don't compute f of 1 or f of negative 1 or anything like that. What we're going to do instead is we're going to use a trick. And so what we're going to do is we're going to take this f and we're going to reduce it modulo some number, and we can choose pretty much any number we want. I'm going to choose 11 because after all, that's the coefficient of n squared. So if we work modulo 11, we don't have to square anything, which is pretty convenient. And so what we're going to do is we're actually going to get a polynomial that's a lot simpler than f, but still has many of the same properties. And by looking for the integer roots of that, we're going to be able to actually find the integer roots of f a lot more computationally efficiently. And so what we're going to do here is we're going to take these coefficients, we're going to put them into a vector, just like that, and then we're going to reduce the components of that vector modulo a number of our choice. And in this case, we'll choose 11. So basically for each of these numbers, we're allowed to add and subtract 11 to our heart's content, And the idea is just to get small numbers coming out the end. So I'm going to subtract 11 to get 0. And for the next component, I'll add 55 to get 1. And then for the last component, I'm going to subtract 33 and I'll get 7. So in particular, we've just learned that f of n is congruent to n plus 7. Okay, that's coming from here. N plus 7 modulo 11. So we've just found this new polynomial that is related to the old polynomial. It's not the same. It's a lot simpler computationally if we want to plug values of n in. And it's going to tell us a lot about what the potential roots of f can be. Okay, so now we just start computing things. Okay, so f of 1 is congruent to n plus 7, which is 8, modulo 11, which is not 0, so 1 couldn't possibly be a root of our original polynomial. F of negative 1 is 6, couldn't possibly be a root. F of 2 is 9, not a root. F of negative 2 is 5, that's not a root. And f of 4, this is where things really get interesting. If we put 4 in here, we get 4 plus 7, which is 11, and we're working modulo 11, so actually that's 0. That's the same thing as 0. So f of 4 is actually congruent to 0 modulo 11. And that tells us that 4 is actually a really good candidate integer root for our original polynomial, right? So these are also candidate roots. All of these are candidates. We got them from the rational root theorem, but most of them aren't very good candidates. And the reason is because we're not getting 0 out here, right? Whereas the moment we get 0, we know that with pretty high probability, that's a genuine integer root. And so now all we have to do is we just have to test that theory. Okay, so let's go ahead and compute f of 4. And so this is 11 times n squared minus 54 times 4 plus 40. And we worked that out earlier, and it turns out that we get 0 there. And so that's really how we know that this 4 needs to come up here and be put into our main solution. Okay, so down here, all this stuff, this was scratch work. And once we've done that, then we can come in here, because we kind of paused here, right? Theoretically, we paused here because we didn't know how to proceed. And so once we've done our scratch work, then we can come back in here and complete our proof and write the final leg of it. All the teacher needs to see is all this stuff above the line, but to actually know how to do that, you need to write this stuff below the line or on a totally different bit of paper. Okay, so we've completed task A. Now we're going to have a look at task B. And that says to find the component of A that is perpendicular to B. Okay, so we've already got the component of A that is parallel to B. And now we need to find the component that's perpendicular to B. So to do that, let's just get rid of all this stuff. We don't need it anymore. And I'll just keep the statement that m is 4 because, you know, we found the correct value for that, so that could be helpful. And in fact, that is helpful because it tells us what b tilde is. So in particular, b tilde equals capital B tilde of m, which is capital B tilde of 4, which is 1, 4, negative 1. And that just came right from the formula for capital B tilde. Now from here, we know that P of M is true, right? So that tells us that the result of projecting onto B of M, the vector A, is negative 11 over 18 B of M. And so in particular, this tells us the result of projecting onto lowercase b, right? Because lowercase b is literally B of M. And so we can actually work this out. We have negative 11 over 18 times 1, 4, negative 1. So here's some helpful notation. Suppose we have a vector space and a vector in that space, let's call it B. If you want to denote the set of all vectors that are orthogonal to B, so in this context it would be a plane. It's the plane going through the origin consisting of all vectors that are orthogonal to B. The standard notation for that is B perp. So what we're trying to do is we're trying to project onto B perp the vector A, and this has to be A minus the projection onto B of A. So let's go ahead and put the numbers in. So we know A, it comes from here, so let's just put that in. It's 2, -3, 1. And we've got the projection of A onto B. It's this, so let's bring this down. It's going to be minus -11 over 18, 1, 4, -1. Let's go ahead and put things over 18. So I'm going to put 1 over 18 out the front here. We need to multiply by 18 now, so we'll get 36, -54, and 18. Two negatives make a positive, so I'll put a plus here, put over 18 here, and I'm going to bring the 11 from the numerator inside here. Okay, so 11, 44, and -11. So now we can bring the 1 over 18 out the front. 36 plus 11, that's 47. -54 plus 44, that's -10. And 18 minus 11 is 7. And so there you have it. We found the projection onto B perp of the vector A.